Hi, I'm Garrett, and this is Lab Group 3A. This week we're doing a lot of image calibration using MATLAB. But what I'm going to do, I'm going to go over all of the physical measurements that we had to take along the optical rail. So first, we're given a detector here, CCD, and the first goal is to get the pixel size and the sensor dimensions. So we're using a microscope with a very low numerical aperture here, and you've essentially just focus until you can see the physical CCD detector. And then you align the crosshair using this translation stage until you're on one edge of the detector, and then simply mark the reading, translate the microscope until you're on the other edge of the detector, and then that's your detector size. It's a very one-to-one translation. And then to get the other dimension, what we did was we just mounted this camera vertically onto the same post and repeated the procedure. So the numbers we came up with, we got dimensions of 6.395 by 4.825 millimeters for our sensor dimensions, which is pretty close to 640 by 480. And then for each, for the sensor, we were able to get the pixel size by just using the MATLAB images. We know that each pixel was there are 640 by 480 pixels in each image. So we were able to obtain, assuming square pixels, that each pixel is 10 microns. And then for the next part of the lab, we needed to analyze a couple of lenses, and as part of this experiment, we need to determine field of view. So here we have a ruler that's exactly 6 inches, and essentially all we do is mark where the camera is, slide the ruler, make sure it's centered on the field of view until the entire ruler takes up the field of view of the camera, and then we know the distance between the camera and the ruler, and we know the length of the ruler. We can compute the geometric horizontal field of view. And for the fisheye lens, we got 178 degree field of view. And for the better lens, we got a 31 degree field of view.
Hi, I'm Jordan. I'm going to talk about the camera calibration right now. So we have a camera down here at the optical rail with the lens mounted onto it, and we were to image this checkerboard at various orientations. So first of all, we did a flat one first off, and then we kind of moved it around. We took multiple images, a minimum of 15, and then we put that data into or uploaded it to our computer. And what Ryan would do then, he would pick one corner here, and kind of go about there, the entire grid, and then we use that data to define where our corners are and what area we want to use to map the distortion effects onto. So for our regular lens, distortions in the negative x direction were negative 0.499, positive x direction were 0.42 or 24, and the negative y direction was 0.005. And in the positive y direction, we had a coefficient of distortion of 0.00173. And our pixel errors were 0.128 in the x direction and 0.124 in the y direction. And for the fisheye lens, we have pixel errors in the negative x direction of negative 0.56, in the positive x of 0.355, in the positive y 0.0251, and in the negative y of negative 0.001133, and pixel errors of plus or minus 0.33 in the x direction and plus or minus 0.428 in the y direction. And lastly, we noticed that if we did not get pixel errors in the range that we wanted, for the regular lens we're looking for pixel errors below 0.1, and for the fisheye we're looking between 0.15 and 0.2. What we did a few times was we had to refine our corners and also take more pictures to get more data points, so that way we can kind of increase our accuracy. That was it.
Hi, I'm Ryan, and this is one of the last parts of the lab where we took this box and we did more or less the same thing that we did with our panel here, except that we took a look at two sides of our box, and the goal is to prove that this is a cube, to show that this is a cubic shape. And to do that, we aimed our two faces of our cube at our camera and oriented the system, calibrated it to characterize this face and this face separately. And what we did is we got a rotation matrix for this face and a rotation matrix for this face. And what we can do is compare those two matrices and find the angle between them. And when we find the angle between them, if that angle is 90 degrees, we've now proven that these two faces are orthogonal to each other. And we prove that this is a cubic shape, at least on this side. If we wanted to completely prove it, we would prove it on all sides. But that would prove our concept. So for our last part of the lab, we were measuring MTF. To do that, we used this slanted box target and aimed it at our camera. And what you want to do is you want to make sure that the middle target is directly in the center of the camera. And I'll show you real fast what happened here. If we take a look at the computer screen, here's the image of our target. You see we have a nice central slant in the middle. And here's our MTF of the middle. The other ones were more or less the same. We didn't see quite as much of a dip at about 0.3 cycles per pixel, but we saw the most pronounced 0 was at 0.3 cycles per pixel. And at half sampling, we went up to about 0.1